Let's get started. We have a flux integral. So we had a chart of all the different types of integrals that we've been talking about. And I'm going to redraw that chart later on. But for now, let's try to remember what a flux integral is. A flux integral is essentially a surface integral. But instead of just a regular function surface, scalar function that goes in there, that's what a surface integral is. We're going to look at this as if it were a vector field. And then we have the surface component for the vector field, which is a normal vector. And this is sometimes written as a surface integral, where the function little f, we would normally call little f, would be here, and then here we have a ds without an arrow on top. So the flux integral can be seen in either of these two ways. And I didn't talk about the relationship here, but I told you guys if you want to look it up, the relationship. This is the unit normal vector of the surface. And then, yeah.
Does that mean that ds has a normal vector?
The ds?
No,
Yeah, well, the normal vector is here, is built into the ds. In fact, that's what I was going to write next here. The ds is equal to the cross product r sub u, or first we say that the surface is parameterized by r, a function of u and v. And remember, the u and the v are just variables. We can look at that as x and y, r and theta, phi and theta, or any other combination of those different variables that would make sense to our parameterization. And then we have the domain, D is the domain in u and v. So once we figure out what u and v is equal to, then we have limits of integration for u and v that would make up our domain. And sometimes it's convenient to write the inequalities if you have constant, if you have a square domain for u and v, or sometimes your u and v described like a circle on the xy plane or something like that, in which case you may want to leave it as d and then go into polar coordinates later on. So the tricky part about this is that there's many ways of doing a problem. You'll see that some ways are easier than others, and it's really up to you starting the problem to figure out which way to go. So anyways, back to the ds. The ds is the cross product of the derivatives, the partial derivatives of the vector that parameterizes your surface. And then I'll put du, dv, but imagine this is in any order that you want. It could be dv, du. And then if we want to look at ds without the arrow on top, this is the magnitude of r sub u. So going back to the surface integral formation, we have the magnitude. So think about what n would equal to in the scenario that we're talking about, and then you'll make the connection that this is actually a normal vector. Now, orientation is important. So we want to say that this is an orientation preserving parameterization. And if it's not an orientation preserving parameterization, if it's the opposite of what you want, then you just throw a negative sign into either the parameterization or into your whole problem, and then you'll be good to go. So given that and this parameterization, I'm going to go with this first definition over here. Just like our line integral, we kind of rewrote that into just a regular integral that we can actually compute, or maybe we kind of looked at it as a path integral, but this is going to be a double integral that we can compute over the domain D of, so you get the f, you evaluated it with x, y, and z in there. You're going to replace it with the x, the y, and the z that came from your parameterization R. So you'll end up having just a function of u and v, and then you're going to dot that with your ds. And then the result that you'll get here will be a function of u and v, a scalar function of u and v that you can integrate over the domain of u and v. So we did a problem real quick at the end of class last time, so I was thinking maybe doing one more problem before going into the next section, just so we get one more flux out of the way. So let's do that.
So that's the breakdown of it.
This is the breakdown, the working definition of the flux integral, yeah. And like I said, depending on how we rewrite our flux integral, we may come up with some shortcuts here and there. So let's see if we can find a problem that might allow us to come up with a shortcut. By the way, the labs are due tonight. They were supposed to be due last night, and I forgot to change the time, so they're due tonight at 11:59.
Thank you.
Thanks for the email. I didn't read the email until 9. Did you send me an email? Or Jose? Oh, thank you.
The most important thing is that you went down to that one time I sent you back with blood.
I still have that.
It's a good one. Good. That was a good picture.
So I think we did number 7. Number 8 is not a flux integral. So we're either 5 or 6. Oh, we did 6. So let's try 5. So I do believe that this homework is due on Sunday, and so that's why I'm doing a few of these things.
Is that a mistake?
What?
We have a bunch of homeworks due. So we have homeworks due Sunday, and then we have
Oh yeah, since it's the last week of classes, I figured we should make the homework due. So instead of Sunday, it's on Wednesday. Yeah, that sounds about right. All right, evaluate the surface integral. So they call it a surface integral, but the way it's set up, the f is bold-faced, the s is bold-faced, so I would think about this as a flux. So evaluate the flux integral of f across the surface S for the closed surfaces using an outward orientation. So here S is the part of the sphere in the first octant oriented toward the origin. Oh, here we didn't. They say for this is a generic question, I guess. So we don't. It's not a closed surface. We're just talking about the front part, the first octant part of the sphere. So not that we need to draw it, but let's say imagine that this is part of a sphere. We're just looking at this first octant part of the sphere. So my first inclination is to think about parameterizing this using spherical coordinates, which would be kind of neat, but then when we start thinking about the cross product of that, I mean the cross product will simplify to the Jacobian, which is kind of like what we did one time. But instead of doing it that way, let me parameterize it. I'll put parameterize in quotes. Parameterize it using what's called the graph parameterization. Start with graph parameterization, which is saying that your parameterization is going to be a function of x and y, and that's x is x, y is y, and then z is this complicated looking thing. So we're just talking about the top half of the hemisphere or top half of the sphere, so that makes it easy to not worry about the negative, positive and negative square roots. And then here, when we talk about the domain, your domain, and just for the sake of drawing it instead of writing equations, I'll just draw a quarter of a circle on the xy plane of radius 9. Okay? All right, so I have the parameterization. I have the vector field over here. And so the next thing to do is to set up our integral. Now, instead of setting up the way I had it set up in the previous slide, instead of using this business over here, I'm going to backtrack and use this and take advantage of the fact that we are, the surface that we're looking at is a sphere, because that's going to give me some pretty good information on the normal. If you have a sphere, imagine what the normal is going to look like. So I'm at the point x, y, z, then the normal is going to be x, y, z, right? So that's a neat thing to try to remember for spheres. And to make sure that this is a unit normal, we just divide by its magnitude. In this case, we're going 9. The sphere is radius 9, so we're going to divide by 9. But for now, let's just put it x squared plus y squared plus z squared under square root. So that's going to give us a neat little shortcut to our flux. Okay? So instead of going by our equation, I'm going to rewrite this flux integral as f dotted with n ds. So I'm going to start off on the side over here, continuing to see if I can simplify before I write it into an integral. Let's take a look at what f dotted with n is going to equal to. If my n is equal to this and my f is equal to this, we have x, negative z, and y dotted with n. And I think at this point I want to lose this business over here because we are integrating over a surface, and the surface is a sphere, a radius 9. So we know that because of a sphere, x squared plus y squared plus z squared is equal to 81, then we can just replace this with a constant. So let's call this 1 over 9. And then now I have x squared. Oh, wait, one of them's a minus, right? Oh, I said it. I probably wrote it. It looks like the z just looks a little bit, the minus sign just kind of blended with my. It does if you look at it closely enough. Where was I? Oh, negative z times y is negative yz, and then y times z is yz again. So it looks like that's going to subtract out. I just have a negative 1/9, not negative, that's just a 1/9 times x squared. Okay? So that's my Fn, f dot n. Now I want to look at my ds. So what's ds equal to? ds is equal to the magnitude of rx by ry cross. Now, is this one of those things that we've seen enough that we should know what it is? So remember that in the graph parameterization, your cross product is just going to be the gradient, and the negative of the gradient in the first two components and a positive 1. Right?
Yeah.
So if you take the derivative with respect to x, this is 1, 0, and then the fx, and then 1, 0, and fy. So what we have here is really the gradient. Now, when you take the derivative, or the magnitude, imagine that this is your little f of xy. So the magnitude is going to be, the negatives are not going to matter, it's going to cancel this. So this is fx squared plus fy squared plus 1. And so we have to imagine taking the derivative of this thing. And this is one of those things that you probably do over and over again. Because you're going to be taking fluxes, a lot of fluxes over spheres and stuff. If you look at the derivative of this, imagine this is a 1/2 power. So it'll be 1/2 this thing to the negative 1/2 power. With me so far? Times the derivative of the inside, which is a negative x, negative 2x. Right? So the 2's would cancel with a 1/2, and then you just have an x on top, and then on top of that you'll square it. So you'll have x squared over this denominator, because the 1/2 got squared. And then you'll do the same thing with the y. You get y squared over the same denominator, which is 81 minus x squared minus y squared. And then plus 1, so if you want to match it up with the denominators, let's see what happens. You got 81 minus x squared minus y squared over 81 minus x squared minus y squared. So the x squareds and y squareds will cancel. I just have an 81 on top with under square root. And then 81 minus x squared minus y squared in the denominator. So that's my ds. So I have my f dot n, and I have my ds, and it's just, I'm just going to multiply it. So I have a double integral over the domain, and keep in mind what the domain was, right? The domain was a quarter circle with radius 9. And my 1/9 x squared times 9 over the square root of 81 minus x squared minus y squared. And then I have dx dy. But I'm going to change my dx dy. Actually, I should have put dA. Can I do that? No, I'll just put dx dy. I'm going to change my dx dy and go to polar coordinates because of d, because our d is a quarter of a circle. So instead of dealing with a quarter of a circle, I'm just going to go ahead directly into polar coordinates. So I'm going to change my x's and y's. My 9's will cancel here. I'm going to change my x's and y's to r cosine theta and r sine theta. So that's my x. And then I have an 81 minus r squared, because x squared plus y squared is equal to r squared. And then my dx dy changes into r dr d theta. And so my theta, outer limits here are constants, going to go from 0 to how far? What? 0 to 9 for my r. R goes from 0 to 9 because that's a radius, and my theta goes from pi over 2. Okay? And that should be a fairly easy integral to compute with some substitution work, or maybe trig substitution, or maybe Wolfram alpha.
Yeah, that's a good one.
So you have to be careful not to call on Wolfram alpha so much, though, because you don't get to use it on the test. But actually, I don't think I'm going to be giving you guys like really difficult integrals on the test anyways. I mean, if you call this difficult. This is a Calc 2. I think this is going to need trig substitution, the r squared under a square root. So I think that might require some trig substitution. But aside from that, it's doable. You still want to do it. So we're going to integrate r to the third cosine theta divided by square root of 81 minus r squared. So the r is already taken care of. We're going to take r from 0 to 9, and then we're going to take theta from 0 to pi over 2. Yeah. Thank you. Hope it'll still come out. All right, so we got something here. I hope it's right. 243 pi over 2. And I suppose since we are stealing this from one of the homework problems, we should see if it's correct or not. Uh, 243 pi over 2. So 243 pi over 2, check. I was trying. Submit. I got that trackpad, so try. Oh, it's wrong. All right, what do we do? So the integral looks right, 81 over r squared. X is the cosine theta, r squared cosine theta, and x squared. Take the dot product right. I hope I did this right. It's 1/2, and the 2x, the 1/2 and the 2 would cancel. Got x squared. This is fx is x over this thing, square root. The y, and then that would cancel with x and y. Square root of 81 is 9. I don't know, can anybody see a mistake? The derivative? I think I did it right. Let's see. So this is, what's our function? Our function f is 81. So it's 1/2 81 minus x squared minus y squared to the negative 1/2. That goes down in the denominator times 2x. So the 2's would cancel, the x would go on top, and then we'll have the square root of this, but then we square it. It becomes x squared. What? Oh. Well, that would cancel with this 2 before we square it. It's in the first octant. Outward orientation. So we have a OPP here, orientation preserving parametrization. Yeah, I don't know. I think this is right. Oh, towards the origin. So I have my orientation going outward. Towards the origin is going inward. So this is not OPP. This is ORP. I'll put that in red. ORP. So this is a reversing parametrization. My orientation, I drew my arrow going outward. If it was going towards the origin, then my normal should have been going inward, which means it's negative. It says here, the first octant with the orientation going towards the origin, and my orientation that I did here was going outside. The end that I found here goes outward. So my orientation is reversing. So that just means I put a negative sign, and I should be right. It should be the same, just negative, I hope. If not, then we're going to quit. Bam! All right, we're still going. Okay. So thank you for reading that, and that's why you should read these problems carefully, because When we're reading flux and line integrals, the line integrals and the flux integrals, the orientation is important. And so whichever way your normal vector, your tangent vectors are pointing is important. And so if you don't want to reparameterize anything, you want to keep your parameterization, but knowing that your parameterization reverses the orientation, then you can follow through with your work, get your answer, except because if your answer is an ORP, because your parameterization's reversing, then your answer is going to be a negative. OPP is orientation preserving, ORP is orientation reversing. We did this one because I drew my arrow going outward, but they want it to go towards the origin. I have an opposite, so that's ORP. So because we have an ORP, our final answer should be negative 243 pi divided by 2. Phew. All right?
Oh, so that's the negative.
The negative is what makes it reverse. All right. Questions? I don't know if they use OPP or ORP in the book.
How would you use it?
What?
How would you use it?
Well, I would look at the orientation that they give, and then I look at the normal or the parameterization that I have, and then I decide whether it's OPP or ORP. And they have this whole discussion about oriented surfaces. And most of the surfaces are orientable, but there's some that are non-orientable surfaces. And we never have to deal with that, so I don't need to talk about it. But you can look in the book, they talk about a Mobius strip. Mobius strip, have you guys heard of Mobius? Mobius strip, that's an example of a non-oriented surface, and you'll see why. Rick?
So which kind of calculate the normal vector?
I got the normal vector because this is something that you can use now. If you have a sphere, a normal vector is a vector that's perpendicular to the surface. If you have a sphere, you have a point on the sphere here, and the normal vector would either be going outward or inward, right? So the outward vector gives you this xyz, so you pretend that you're in a point xyz. You can pretend you're at the point 1, 0, 0 right here. And so your normal vector is going in the same direction as that point from the origin. And so your normal vector is going, the outward normal vector is going to be the same as the actual point xyz that you're on. Now, to make it, because n in this scenario is a unit normal vector, you just need to divide by x squared plus y squared plus z squared. But if you're on a sphere already, then your x squared plus y squared plus z squared, you're just going to divide by the magnitude of the radius. And so that's what we did. We divided by 9. So that's how we got our, well, this turned out to be 9. So that's how we got our normal vector. Well, for other surfaces, our normal vector is going to be a lot more confusing. So for non-spherical surfaces, we probably want to just try to parameterize. Like if your surface is a cone or something like that, then you probably want to. You don't have any special shortcuts for the normal vector. This is really, this n over here is really just a shortcut for the sphere. Any other questions?
If we were to do it without doing the normal vector, but going back to the angles r dotted with the RU
Yeah.
V, we would,
You get the same answer.
yeah, but it would just be a matter of putting in the original r vector
Yeah, so you would put this R vector into this.
So we would just basically be replacing the negative z with the negative square root law.
Right,
Okay.
right. And then you'll see that when you dot it with this, without the magnitude, when you dot it with this thing, then you'll see it cancel the same way it canceled over here.
Got it. Why is there a flux?
Say it again.
Why is there like two dimensions?
Why is there two?
What's the difference between this one and the other one?
Oh, well, this one is still a flux, but you're reducing your vector field into a scalar function. This is our scalar function. You're reducing this f dot n into this scalar function, which is now going to be just a regular double integral.
Is there any reason why we wouldn't be able to calculate it?
Well, you can calculate, like Lauren was saying, you can calculate it the other way, except it might be a little bit more difficult. You might have to be carrying the parameterization a little bit more than you have to.
Much like conversing into polar, it seems like one method is just a couple more steps. It's doable either way, it's just a matter of one thing that you there's just so many more steps, which then gives you so many more negative signs to keep track of.
Yeah, and so if we parameterize this using spherical coordinates with phi and theta, you'll see that when we do this cross product, we're going to come up with like a bunch of x sine squared plus cosine squareds with phis and thetas, and it'll all simplify, but it'll just look a little bit messier in your work.
And that we tell us use the flux for this, or
Maybe.
we make it easy
I think because of time constraints on the test, I'll tell you to use specific theorems to simplify things. Okay. Any questions? Those are good questions. And and really, the best way to do this is to try problems on your own. So now you only have one flux integral to do. I mean, you still have to redo this again. But I did this flux integral. I did another one at the end of last class. And so there's one flux integral left in this homework set. So if you feel like you probably want a little bit more practice, you can start by going over the examples that they have in the book and just following along, and then maybe try one more and then check your answer in the back or something. Okay? Just for good practice. All right. Still talking about flux integrals. We're going to change our viewpoint a little bit and change our problem using a special where's my cap lock? Special flux. Sounds romantic. What we're going to do is we're going to consider a flux integral. Actually, let me just tell you what this is. This is really just jumping to Stokes' theorem. So let me just say Stokes' theorem. Well, we can keep that there too. Kind of feeling sorry for you now. All right, so Stokes' theorem looks at a flux integral, but not just a regular flux, it's a special flux. So remember, a flux integral is over a surface of ds, but it's looking at a special kind of vector field. So the vector field that it's going to consider is a curl. of a vector field. So remember, when you take the curl of a vector field, you're going to get a vector field because, you know, when you cross two vectors, you get another vector. So this is still going to be a vector field. So the curl of a vector field over a surface S is what we're going to consider. Now what we're going to do is we're going to imagine that we have an open surface. An open surface is a surface that's not closed. What? Well, yeah, right?
Well, wasn't that quarter of a sphere?
That's an open surface. Yeah. If we had to find the flux over the whole sphere, then that's a closed surface. Okay? So if we look at the quarter sphere that we just did, or this generic upside down jar, I don't know what this is. This is a surface with that's not closed. That's the big thing. Or somebody, yeah.
Or something.
Stokes theorem is specifically for an open surface.
Stokes' theorem, yes, is for specifically an open surface. And so this is Stokes' theorem. So Stokes' theorem says that if you're looking for a flux of a curl over an open surface like this, that this is going to reduce down to a single integral. And the single integral is more specifically going to be a line integral over a curve S. Now, I'm going to replace this C with something, if you guys are taking notes in pencil. And instead of looking at the curl of this, instead of taking the flux of the curl, we're going to take the line integral of the original vector field, ds. And so there's some dot products here that I can make more obvious. These are both dot products. What is C? What would you guess C would be?
The parameterization of the line.
Line? What line?
The vector.
What? What curve? Surface. What surface? No. What surface? What about the surface?
The open.
Oh, yes, the open surface. We have an open surface. Now, this is a line integral, so C has to be a curve.
The curve will be the curl.
The what? Close. The outside of the what? Oh, the outside of the jar,
Outside path.
right? What would be a good name for the outside of the jar? Well, it's not a surface. This is a C, right? It's a curve. What would be a good name for this? The mouth. Closer, yeah, it's the mouth of the jar. The opening? All right. It's called the boundary. So I'm going to move this C down a little bit and then call it the boundary of S. Now that looks like a partial notation. What are you doing? That's the notation that they use for the boundary. C is the boundary of S. So if your surface is open, it's necessarily going to have a boundary, right? Like that example that we had with the quarter of a sphere. This is going to have a boundary, right? The boundary is going to be, well, it's going to be in three pieces, it looks like. It's going to be this piece of a circle here, another piece of a circle here, and then another piece of a circle here.
How do we not care about the bounded sections that are the inside, so the axis lengths?
No, because that's not part of the surface. The surface itself is just
Okay.
the thing, the quarter sphere, or the eighth of the sphere, right? So all we care about is with respect to that surface. Now there's one more issue to deal with here. What? No? The what? No? In terms of the surface and the curve, and the types of integrals that we're dealing with, one of them is a flux, one of them is a line integral. So what are we concerned about whenever we're dealing with a flux and a line integral? We're parameterizing it. What do we need to know about the parameterization?
When it starts from in.
Okay, so what about it? No. So what did we get wrong in the last problem? The orientation. So a flux has an orientation for the surface, and the line integral has an orientation for the curve. So the orientation is going to be important. Now, how can we relate the orientation for the surface with the orientation for the curve? Now, let's imagine an orientation here for this upside down Winnie the Pooh jar business that we have. Let's give it an orientation. So it's up to us, or it's up to somebody, whoever's making up the problem, whether they want the orientation to be looking like it's going in or out. Okay, so let's say the orientation was just going out, just so I can draw it. Then how is this orientation, how is this outward orientation for the surface going to affect the orientation for the curve? So what we want to do when we're looking at relating the orientation of the surface and the orientation of its boundary is we're going to use our right-hand rule, right? So using our right hand, imagine how the orientation would give us that normal vector that points in our right thumb direction. All right? So I would draw like an orientation that goes around this way. Now let's move this closer and closer to the boundary. And if you move it closer to the boundary, can you see that this boundary is going to, the curve is going to go in a specific direction based on the orientation of the surface? So I get closer and closer to the boundary. It looks like my right thumb pointing up is going to make this curve go in a specific direction. So it looks like my direction, the orientation for my line integral, will end up going this way. The right-hand rule, you take your fingers and you wrap it around something, and your fingers, the direction of which way your fingers are going is the direction that you're moving along the surface, so to speak. So if you get a jar, anybody have a jar? Here, I have a cap.
Water bottle? Is the water bottle there?
Let's use a cap. So let's say we have an outward orientation, right? It's going this way. So if you wrap your right hand, finger is going this way. As you get closer to the cap, or to the boundary, you're going to kind of push this line to go in this direction, right? If you have an inward orientation, then you're inside of the cap going this way, and if you look at how that goes around, you're going to push the direction of the line, the boundary, in the other direction as opposed to the outward. So, if we take a look at that idea with this surface, and we take a look at the correct orientation that we had for the problem that we did before this one, let's take a look at this, and I think I need to redraw this a little bit. So I'm going to redraw it like this so that I can see my normal vector, because a normal vector is supposed to point towards the origin, right? Can you see this? This is idea. I think I need to make it bigger. So I think maybe if I make it a little bit bigger, my normal vector points towards the origin. And so if it points towards the origin, I take my right hand and I want to know which way is this curve going to go. Is it going to go up or is it going to go down? Using your right hand rule on this normal vector that's by that edge, which way is are your right fingers going to move this curve? Up. I was thinking up. Because if you imagine your thumb is in the direction of this, your right thumb is in the direction of this red arrow down here, your fingers are going to make this curl upward. Okay? Yeah. If it's on top, well, if this had an outward normal, then your rotation is going to make it go down. But we don't have an outward normal, we have an inward normal. And so those normal vectors is going to make it curve up. And so now that we got one curve, the orientation for one curve, then we can figure out the rest of them. Okay? So does the orientation make sense? Is that a normal vector with your right hand? This is a thumbs up.
This is why Math doesn't make sense.
What? Stokes. This is Stokes' theorem. So the idea behind Stokes' theorem is that you have two integrals to deal with. Okay? And a typical problem might be you have one integral and this looks like it might be too hard, so maybe we'll do it the other way. Or if you have this integral, if you're doing a flux integral of a curl of something, instead of trying to do that directly, which means take the curl and then parameterize the surface and then check if it's OPP or RP and then take the dot product and do a surface integral, instead of doing it like that, maybe a line integral might be easier. So maybe finding out what the boundary is and then working it out that way. Okay? So that's the first general idea of Stokes' theorem. Now the next general idea of Stokes' theorem is that if this is true, let me rewrite Stokes' theorem on another page over here. It's just a single integral over the boundary of the surface. So you're trading a flux integral for a line integral or vice versa. Now let's say you start off with a hemisphere so that your boundary is a circle, right? So this is your S, and this is your, maybe I'll label it differently. This is your S, and then this, oh, I put the boundary in blue, so let's put this in blue. It's a boundary of S, right? Now, if this statement is true, I can keep that same boundary and I can change my surface. What if I just had a flat disk? Let's call this S1. Then this should still be okay. So I can still do a flux integral of S1 of the curl of my vector field dotted with ds. And that should still be equal to these two things, right? So if instead of doing this with a hemisphere, this disk over here has the same boundary as that hemisphere, as long as I'm on the right orientation, then I might have a simpler integral to deal with. In fact, I can use any surface that I want as long as it has the same boundary. It should still work out okay, right? Of course, I'm not going to trade in a more complicated surface. I might want to trade in a simpler surface with a flat disk instead of a hemisphere or a paraboloid or anything for that matter that has that boundary. So I can trade in a simpler surface to do this integral. So that's another aspect of Stokes' theorem. What? How would it look? Well, let's say you're doing this. This is really the extent of it. Let's say you had to find this this flux of the curl of this function over a hemisphere, right? Well, if that trying to parameterize this hemisphere looks a little bit more complicated, what if I just parameterize a disk instead? So a disk is easier to deal with. This S1 over here would have an X and a Y and a 0 for a Z. The 0 for a Z really would make a difference for a lot of computation. Whenever the more zeros that you have, the better, the easier it might be. So that might help us simplify our integral instead of whatever the parameterization for this was. Remember what it was? It was like x, y, and then the square root of whatever. So that's just a graph parameterization, and then later on you might be interested in turning it into spherical or cylindrical or whatever. You should get the same answer according to Stokes' theorem. Yeah. And it's not from here to here directly, it's kind of from here to a line integral, but wait, instead of doing it over that line, I have another surface that's simpler. Maybe I'll use that instead, and so that's how you make that connection. So those are the two main aspects of Stokes' theorem in general. And what we're going to do next time is we'll take a look at examples where it might have been easier, instead of doing the flux of a curl, maybe take the original field. It might be easier to do a line integral instead. Or it might be easier to pick another surface with the same boundary to see how that would look like. Okay? All right, so next time we'll do that real quick, and then we'll jump into the last the last section. Oh, you guys have a quiz. Well, there's no time now. Let me show you real quick. It's online. It's on our last section. No, you guys will probably have one more. Take-home quiz number 11. It's down here. So this is using surface integral and the flux integral. All right. Good luck.